Okay, this is for Physics 5B. This is August 11th, 2020. This is the lab we're going to do just to finish things off. I'm going to do the whole thing on the video. But you still want to turn it in, so I got something for you that we did this lab. So basically the way to get to where we're going to use all these simulations, you just go to Google, just put in PHET. That's it. Then you click on free online physics, chemistry, biology, earth science, all these tons of stuff. Okay, but we're just going to look at the physics ones because this is a physics class. You come up here to simulations, you got physics right there. You can see all the other ones as well. You can check those out. We go to physics. Okay, and then here are all the simulations. There's a ton of them. Okay, some of them we can't run on Sac State computers. The ones that are Java, Sac State has made it so their virus stuff apparently won't run Java at all. I can't run Java on this thing. But we can run all these guys here, the HTML5. Okay, I wish more of these were, all of these were written in that. All right, so we go over to the lab. The lab is, here are the modules. The lab is here. Okay, so if you don't have the lab, you want to hit pause and go download the lab. There it is right there. And I gave you, I'm now, what is that, published? Oh. So now you got homework 7, we do the day of the exam, then the lab, I mean, we're going to do it right now. All you've got to do is watch this video. You can do the whole lab, okay? There's the lab right there. You can download it there. I don't know what this green thing means. It doesn't go all the way down. It goes all the way down over here. I don't know why that's not, it's published. Unpublished. What? It's okay, it was published. Okay, so it's right here. So here is the lab. And basically, it starts with this one called John Voltage. That's what it's called. If you click here, or you click the picture, it should take you right to the John Voltage thing. So John Voltage is down here. It's all in alphabetical order. There's John Voltage. And you hit play. And when you scruff John Travolta's feet, what happens? He picks up electrons. He picks up negative charge. You keep doing it. Now finally, the whole mess of these things on here, finally, there's a discharge. Okay? But if you move the arm closer, you don't need so much. But there. See, that wasn't quite as much. Move it really close. Practically touching it. Oop, gotta see the little more on that. There we go. But if you have it way up here where it was originally, it'll take a while. That may even be too far away. There we go, finally. Okay, so if we take a look at the questions we had here, scrape John Travolta's feet across the rug. What happens? He gains negative charge. Electrons left the rug and went up into John Travolta. Okay, without moving John Travolta's arm, keep scruffing his foot on the rug as he builds up more and more negative charge. How much charge does he take to build up on him before he discharges into the doorknob? A lot, not much, very little, a lot. We had to put a lot on there before it actually discharged. Then we moved his finger closer to the doorknob. Does it take more or less charge to build up on his body before he discharges again? It took less once he was a little bit closer. Okay, so hold on. Okay, so what happens? Electrons went onto his body. Negative charge went onto his body. Okay, we had to put a lot on there before he discharged, and then we moved the finger closer. It didn't take. It took less charge on his body before it discharges. Okay, balloons and static charge. So now we want to do. It's called balloons and static charge. You can. I think you can. How come it's not showing up? Oh, there it showed up finally. Okay, there it is. That should be on the picture too. Okay. Okay, so this one's going to be right here. Again, they're in alphabetical order. You can either click on that. I'm just going to do it this way. So you got balloons up here. There it is. Okay, so you got your yellow balloon, you got your wool sweater, rubber balloon, you got a wall over here. Okay, so let's go ahead and see what it says to do. Move the neutral balloon near the sweater. Does anything happen? So we move the neutral balloon towards the sweater. Nope, nothing. Oh, I've got to reset this now. So it's a neutral balloon. Okay, so now move the neutral balloon close to the wall. We did that too, nothing happened. Do it both ways. Towards the sweater, towards the wall. Nothing, 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 nothing. Okay. Rub the balloon on the wool 2 or 3 times. What happens? Okay, so we rub the balloon on the wool. 1, 2, 3. Okay, so now what happens? Oops, now the balloon is being attracted to the sweater. The balloon is negatively charged, the sweater is now positively charged. We took electrons away from the sweater and put them onto the balloon. So rub the rubber balloon on the wool 3 or 4 times. What happens? Well, now electrons left the sweater and went onto the rubber balloon. The positive charges didn't do anything. Okay, the positive charges stayed stationary. Is the balloon now attracted or repelled by the sweater? It's attracted to the sweater. Why does the balloon behave in this way? Because now the sweater is positively charged, the balloon is negatively charged. And that's why we saw the balloon behave in that way. Now bring the balloon near the wall. How did the charged particles in the wall react? So we've got to grab that balloon. Watch the negative charges. They are moving away slightly. See how they move away? Okay, now what that means is the repulsive force between the negative charges decreases because there's greater distance between them. The positive charges, which is in the nucleus, they're not going to move much. Okay, they may move a little bit forward, but then the attractive force between the positive and the negative is going to be greater than the repulsive force between the negative and the negative, and this is what happens. It sticks to the wall. This is negatively charged. The negative charge moved away. The wall is not charged. The wall is neutral. Okay, but by moving the balloon over there, we move the negative charges away, and that causes basically the Coulomb forces. The one that's attractive between the positives and the negatives is greater than the repulsive one between the negatives and the negatives. So that's why the balloon's stuck there. Okay, so how did the charged particles in the wall react? Well, the negative charges moved away from the balloon. Move the balloon away from the wall so that the balloon is more attracted to the sweater than the wall. Is this a short distance from the wall or a long distance from the wall? All right, so we come up over here and we move the balloon, say, to there. Boom, goes towards the wall, to there. Boom, now it drifted over towards the sweater. So the the further you move it away too, look, there's the electrons aren't as far away. So right about it here someplace, it moves towards the sweater there, then it moves to the wall. So it's right in there, so it's a short distance, very short distance. Okay, so it's a short distance for this one. Click the reset so you have a neutral yellow balloon and remove the wall. So you come over here and you reset and you remove the wall. Okay. Okay, click on the icon showing 2 balloons so a neutral green balloon joins your neutral yellow balloon. That's this guy right here. So now we got 2. And nothing happens. They're not attracted, they're not repelled, nothing. Is there any attraction between the 2 balloons? While they're neutral, no, there's no attraction. Rub rubber balloon on the sweater, again, to negatively charge it. So I'm going to go back over here, take the rubber balloon, and rub it here. Now it's negatively charged. And there might be a little bit of polarization between them, but the simulation's not showing that. It's showing that they're not attracted to each other. It's still, or repelled by each other even, right? Because if they're repelled, the green balloon would move away. But it's not, but the yellow balloon's still attracted towards the sweater. Okay, so rub the rubber balloon. Okay, so no, there's nothing between the balloons still. Now rub, so this has to do with maybe there's a little bit of polarization in the green balloon, but the simulation doesn't show that. Now rub the green balloon on the sweater. What happens to the green balloon? Well, we kind of already know the green balloon is going to pick up electrons. So now the green balloon is negatively charged as well. Okay, now rub the green balloon. So what happened to the green balloon? It picked up negative charge. It picked up electrons and became negatively charged. Now, do the 2 balloons attract or repel each other? Well, let's go and see. No. See what happens there? If I put this balloon there, it drifts away slowly. that I move it close, boom, it runs away as fast as it can get. So we could say they're repelling each other. See, they're repelling each other, repelling each other, repelling each other. Okay, so they're repelling each other. They're both negatively charged. Okay, so the two balloons repel each other now. Why is this? They're both negatively charged, and like charges repel. Okay, now we'll move on to charges and fields. So we go back over to our PHET. Go back again. They're in alphabetical order, so look for charges. Oh. Okay. Okay, so here we have it. So it's going to tell us to put the positive one out first. How do I know that? Because I wrote it. So, okay, place the +1 nanocoulomb charge in the middle of the field vertically and a bit to the left horizontally. Okay, so there it is. I placed it in right about in the middle and to the left. Do the electric field lines point towards or away from this positive charge? They would point away from it. They point away from the positive charge. Okay. Now place the -1 nanocoulomb charge in the middle of the field vertically and a bit to the right horizontally. Okay, so we can place this over here. Okay, they're still pointing away from the positive, but they're pointing in towards the negative. Okay, if I take that away, oops, there we go, we got rid of it. Okay, now also basically what these guys are, they're showing you how, see these are bright, these are the field lines. These are very bright, and they get dimmer over here. That's supposed to show you the strength of the field at those places. If I go direction only, then they show all this stuff without any distinction. Okay, but now they're trying to show you the strength of the electric field that way. So now we've got these two charges. Okay, in what direction are the field lines pointing now? Away from both charges, away from the positive, towards the negative. So they're pointing away from the positive and they're pointing towards the negative charge. Okay, so there they are right now, pointing away from positive but towards the negative charge. That's the direction we've been drawing the electric field. Okay, is there any point between the charges where the voltage is 0? Okay, so we've got this voltmeter here. Okay, we take it out. There's a bunch of stuff I had in there that I deleted. Okay, so we can, because it's so hard to get the right, this is supposed to be at 1000 and minus 170 volts. It's hard to find it. Okay, we might be able to find it on the positive over here a little better, but I doubt it. Took me a while to find it. But anyway, forget, there it is right there. That's what it's supposed to be. That's the maximum voltage, but it's so hard to get it. So let's forget about that. I took that all out. So let's find a place where, let's see, we got +3, +2, +1, +0, and then boom, we're negative. So right in here someplace, yes, there is a place where we have 0 voltage right between those two. Okay? Okay, is there a point between the charges where the voltage is 0? So try your best to find it. We just kind of looked at it. So now recall that the electric field equals change in voltage over change in distance. Place the voltmeter at a point where the voltage is around 6 volts. Make sure values is checked in the upper box. So we're going to do this. We got values here. We're going to place the voltmeter someplace where we get 6 volts. So there's 4, there's 3, there's, I saw 6. Go back, go back, go back. Okay. 6.034, that's close enough. And you click on this, I guess it's a pencil, I don't know. Click on that, and it gives us this circle. And it's about 6.0 volts. All the way around this circle is 6.0 volts. That's an equipotential surface that we learned about earlier in the semester. Equipotential surface. And we go around here, it's going to be, there's like about 5.8. There's going to be, it's about 6 volts. It moves very, very slowly. I wish they didn't have so many digits of accuracy. There's about 6 there. There's about 60 there. That's close enough. 6.0 there. So it's all about 6 volts all the way around here. That's equipotential surface in which the voltages are all the same. Okay. Okay, so let's see. Pencil icon, we did that. A circle appears. The circle is known as the equipotential surface. The volt. Okay, so we did all that. Place the voltmeter at a point where the voltage is around 1 volt, and we'll do the same thing. So click on that. So I put this someplace where I'm trying to find 1 volt. So there's -2, there's 1, so let's go back to this way. There's about, right about there, it's about, so we'll do the pencil again. And now we've got the second one, it's 1.0 volts. There we have them, okay? 6 volts here, 1 volt there. Okay, so now we've done that. Okay, measure, so 1 volt. Click on the icon with the, okay. Now you have an equally potential surface where the voltage is 1 volt all the way around. So if you were to take the voltmeter and go all the way around here, it's going to be around 1 volt the whole way. There's 1.004, there's 0.985. It's all pretty much right around 1 volt. Okay, I'll go up here. We'll get the same thing. 1 point. So anyway, so hopefully you're convinced. Okay. Measure the distance between the 2 surfaces right between the 2 charges. Use this to calculate the electric field at this point. So I'm going to come over here and I'm going to grab this guy. This is a tape measure. So I'll put him right there at the 6 volt. Now this is right down the middle, okay? And I'll yank this guy out. And that distance is 57.8 centimeters, 57 or 0.578 meters. So we've got a difference of 5 volts. Remember, it's delta V over delta X. Delta V is going to be 5 volts, and delta X is going to be 0.578 meters. So what I'm going to do now is I'm going to do this. I'm going to put a mathematical equation in there, but it's going to take too long. I don't want to waste time. So let me pause it now. Okay, so what I did was I put in the equation here. So you've got the electric field is going to be equal to change in voltage over change in X, the change in, or the distance. We had that from early on in the semester. You got your 5 volts, your 6 volts minus your 1 volt. Then we had the distance of 0.578. So it'd be 57.8 centimeters, 0.578 meters. Okay, and that came out to be 8.65 volts per meter. So that was the strength of the electric field. Now we want to choose a point further out. Okay, so we'll go back here. I'll take the tape measure. So we'll put the tape measure, say, like right here. What we want to do is, though, we want to follow the electric field lines. So I'm going to take the tape measure. We don't want to just do this. That's not right, because we're not following. The electric field lines are going this way. So you want to go up like this. So we're kind of following. We can't do it perfect. Put a little string down there to get the curvature. We're doing it as best we can. Okay. So now the distance is what is that? 100 over a meter. So it's 106.5 centimeters. It's 1.07 meters. We'll call it 1.07 meters. Okay, so I'm going to do the same thing now. I'm going to come back over here, 1.07 meters, and then went down to the next page. Okay, well anyway, so what I'm going to do now is do the pause, and when you come back to see the... Okay, so our change in voltage was still 5 volts, but now we had a distance of 1.07 meters. Okay, remember that? It was 106.5 centimeters, which would be about 1.07 meters. And now we would get only 4.67 volts per meter compared to the 8.65 we had down the middle. Okay, is there a difference in the field strength? Yes. Where is the field stronger? In the middle. So the field is actually weaker out here. Okay, the electric field lines are more separated a little bit, so it's weaker out. You can see them getting dimmer. These guys are all nice and bright down the middle, right? Okay, well we got here, they get dimmer and dimmer. That's supposed to represent the strength of the magnetic field. Okay, so now we want to go to Ohm's law simulation. So once again, let me go, is there an alphabetical order? Go down to the O's. Ohm's law simulation. Okay, so what you can do is you can mess with the voltage and you can mess with resistance and see what happens with the current. Right now we got 4.5 volts, 500 ohms. That's going to give us 9.0 milliamps. So if you go, so remember Ohm's law, V equals I times R. I is going to equal V over R. So you take 4.5 volts divided by 500, you get 0.009 amps or 9.0 milliamps. So let's see, if we mess with the voltage, we slide it up, oh, the current goes up. See it going up, the letter's getting bigger. Slide it down, it gets smaller. Okay, and then let's see, can I get it back to where it was? So there we have our 9 amps again, or 9 milliamps. Now what about the resistance? Increase the resistance, oh, it gets smaller, it's the opposite. Go the other way, decrease resistance, it gets bigger, okay? So, move the voltage slider up and down, how does the current react? When we move it up, the current increases. When we move it down, the current decreases. Move it up, current increases. Move it down, current decreases. What can we say about the relationship between the current and the voltage? They're directly related. As voltage goes up, current goes up if we keep the resistance the same. Move the resistance slider up and down, how does the current react? When the resistance slider goes up, the current goes down. When the resistance slider goes down, the current goes up. What can we say about the relationship between the current and the resistance? They're inversely related. As the resistance goes up, the current goes down. As the resistance goes down, the current goes up. That's the I equals V over R. So I is directly related to voltage and inversely related to the resistance. Oh, I didn't make this one clickable, did I? Well, resistance in a wire. Darn it, I forgot about. Oh, the picture is. I just didn't. The picture is, but this isn't. This isn't. But the picture is. Make sure. Link. It's not. I'll tell you what. I'll fix that and I'll upload it again. All right, so I can make this. So anyway, what we want to do is come over here, resistance in a wire. So we go back. I wish this would go back to where we were, but it goes back to the top every time. What's that? We're good, I guess. We're recording. All right, so let's go back to resistance in a wire. Resistance in a wire. So once again, we open it. Okay, so resistivity. What happens to the resistance? Here's our wire. What is the resistance in that wire? Now remember, the resistivity depends on what the material it's made out of. Like copper, silver, those guys have very low resistivities. They're very good conductors, so our resistance is lower because of that. But things like wood, I can't remember which one we had that was a huge resistivity, but they have high resistivities because they're not good conductors. So if the resistivity is high, like for a piece of wood or something like that, boom, the resistance goes up. But if it's like copper or something like that, the resistivity goes down, then it gets low. Okay, so the resistivity, as we increase the resistivity, the resistance increases. As we decrease the resistivity, the resistance decreases. So move the resistivity slider up and down. How does the resistance react? What can we say about the relationship between resistance and resistivity? Okay, so as they're directly related to each other. As resistivity goes up, the resistance of the wire goes up. As the resistivity goes down, the resistance of the wire goes down. And it just depends what the wire is made out of. Okay, so now let's do the length. Slide up. Resistance goes up as length goes up. Resistance goes down as length goes down. Well, look at it this way. The electrons have to go from here to here, okay? So that's going to be the resistance they're going to. So if we increase the length they have to travel, that's more things for them to get in trouble with, okay? That's more obstacles in their way. If we put it down, it gets shorter and shorter, then obviously they have less trouble. They have less obstacles in their way. So that's why it makes so much sense there. Okay, now let's just do area real quick. We see areas on the bottom, so we know how that's going to go. Make the area big, resistance goes down, because now you've got more cross-sectional area, more room to move through. Make the area small, and the resistance goes way up. Okay, resistance goes up. So now we can go back and start answering some of these questions. Move the slider up and down. How does resistance react? So this is for the length slider. As the length gets larger, the resistance goes up. As the length gets shorter, the resistance goes down. What can we say about the relationship between the resistance and the length? That they're directly related. Greater length means greater resistance. Why might this be the case? Because longer length means the longer distance electrons have to go, and there are more places for them to lose energy and smash into nucleuses and so on. move the area up and down, area slider up and down. How does the resistance react? Well, the resistance, if you make the area bigger, the resistance goes down. They're inversely related. What can you say about the relationship between the resistance and area? That they're inversely related. Greater area means smaller resistance, smaller area means greater resistance. Why might this be the case? Because the greater the area, the greater cross-sectional area there is, the more room electrons have to flow. So that's why that is. Okay, so now we got Capacitors Basic Lab, and these should both take you to the Capacitor Basic Lab. So we come over here, do it this way, we go back, back. So CAP, going to be up here. Capacitor Basic Lab. We don't want Capacitor Lab, we want Capacitor Lab Basics. Okay, so there's our capacitor. So let's see what we're supposed to do here. Okay, recall that the capacitance C in farads is equal to charge Q in coulombs divided by the volts V in volts. Okay, check the electric field in the upper right-hand box. So if you come back over here, you got electric field here. So we got them all checked. Place the voltmeter to measure the voltage across the capacitor. So we take our voltmeter, we put one like here, one down here, 0 volts. Use a slider on the battery to place a voltage of 0.5 volts across the capacitor. Here's the slider. So I move it up, and there's 0.5, there's 0.1, 0.5 is right there. It said 0.5, right? Yeah, 0.5 volts. So now we got the 0.5 volts across the capacitor. Okay. What is the charge on the capacitor shown in the box in the upper left? So we got to do this. We got to click on that, and it's 0.15 picocoulombs. Okay, picocoulombs. Use this charge along with the voltage across the capacitor to calculate the capacitance of the capacitor. Are you close? Okay, so what I'm going to do is use this equation right here. And I'm going to put when you come back, you'll have an equation right there. I don't want to do it live because it takes so long. Okay, so let me hit pause. Okay, so we had 0.15 picocoulombs. That was the top. So both of these are going to be 0.5 picocoulombs, okay? So this is going to be plus 0.15 picocoulombs. This is going to be minus 0.15 picocoulombs. So that was the charge. We had 0.5 volts. Okay, so it's the Q divided by the V. There they are right there. We get 3.0 times 10 to the minus 13. Oops, I forgot to put. This is going to be farads. Okay, which is equal to 0.30 picofarads, which is what the capacitance is right there. Okay, so it worked. Okay, that's it for this, but I just want you to notice we could change the capacitor. If I'd gotten on top of it and I didn't have all those classes at Sac City, we would have done more with this. Because I can change the capacitance there, I can change the charge, I can change the area. Well, that's all further they'll let me go, huh? Or change the area. So I can change the area, change the distance between the plates, and other stuff here. Okay, so anyway, there's a whole lot more we could have done with this lab. All right, so let me go and find out where we're going next. Okay, so this is, okay, construction circuit, circuit construction kit DC. So what we do is we go back over here, go to circuit, there we go right there. We want this one right here. Circuit construction kit DC. So the first thing it's going to tell us to do is build we want an intro. Put a battery, got to get it from over here. Put a battery there. Put a wire there. Put another wire there. Put a resistor in the circuit. We're going to use a light bulb. This is your resistance. This is a resistor too, but this guy lights up, so it's a little bit cooler. This guy over a little bit. So he's right next to the battery. So that's how you build the circuit. Now you got your electrons flowing, you got your light turned on. You can check what the battery is. The battery, well, actually, we can check the battery. So we got the voltmeter here. Take the voltmeter down, and across the battery is going to be 9.00 volts. We can take this guy over here, and there it's going to be 0.90 amps. So over here we also have 9 volts. You move this guy around, you're going to measure 0.9 amps everywhere. Okay, so the current's the same everywhere in this circuit right here. And if we click on there, we can see that it wasn't a right click, it's just a regular click. Just click on it directly. So it's going to be 10 ohms, so that guy's 10 ohms, all right? Oops, I didn't mean to do that. I meant to... What in the heck is going on now? Hold on. Okay, we're sort of fixed now. All right, so let's see here. So build a simple circuit with a battery, light bulb. That's the resistance and wire. So we just did that. Use the voltmeter to measure the voltages across the battery and then across the light bulb. What are the values? They're both 9 volts. Are they equal? Yes. Check on the light bulb to see its resistance. We did. That was 10 ohms. Just click on it. 10 ohms. Using Ohm's law, V equals I times R, find the current in this circuit. All right, so what we're going to do is go I equals V over R. So when you come back, let me do this. When we come back, you will see the equation there for that. Okay, so we got out of it with 0.9 amps, 9 volts, that's the voltage from the battery, that's the voltage across the resistor, 10 ohms, so 9 volts divided by 10 ohms, 0.9 amps. If we go back over here, 0.9 amps, oops, it's 0.9 amps, yeah, 0.9 amps. So 0.9 amps everywhere, so there we go. Okay, we already have the ammeter. Measure the current in the circuit. Does this measurement agree with the calculation you just did? Yes, it agrees. I didn't have you grab the ammeter, I grabbed it already. All right, so yes, 0.9 amps, it does agree. Use the resistance slider to change the resistance of the bulb to 20 ohms. So we'll come over here and we will use this guy and watch what happens to the current. We'll go from 10 ohms to right around 20 ohms. We're down to, we were at, let's see if I can get it exactly 20. So we were at 0.9, now we're down to 0.45, exactly half. So our current was cut in half when we doubled the resistance. Okay, the next thing it's going to ask you to do is change the resistance to 5 ohms. Now at 10 ohms is 0.9 amps. Now at 5 ohms it's 1.8 amps. It's doubled. It doubled there. Okay, so we can answer these questions now. So when we change it to 20 ohms, what happens to the current? It was cut in half. It went from 0.9 amps to 0.45 amps. When we change it to 5 ohms, it went from, say, 9 amps up to 1.8 amps. It doubled because we decreased the resistance. Okay, slide the resistance back to 10 ohms and add a second resistor in series. Okay, so we do that by, okay, we'll make this back to 10. Okay, then what we want to do is we want to break this. Okay, there we go. So if you click on that, it'll give you scissors. So there, broke it. I can kind of get this stuff kind of out of the way. Move this back over here. Grab a wire. Put that there. Grab another light bulb. Put that there. Grab this guy. Put that guy there. Okay, now you're going to see that it's been cut in half to 0.45 amps. This guy is 10 ohms. This guy is 10 ohms. Remember, you add them in series, it's going to be 20 ohms. That's the same as our 120 ohm light bulb by itself. Okay, so let's put it up. We can read the voltage here. Okay, add a second resistor. Measure the voltage across both light bulbs. We got 9 volts here. We've got 4.5 volts across this guy. 9 volts across both of them. 4.5 volts across this guy. So now they share the voltage. They sum up to the 9 volts. They sum up to the 9 volts. The current stays the same everywhere. It's a new current. It's not 0.9, it's 0.45, but it's going to be 0.45 everywhere. Okay, now we measure the, okay, what are they? They're 4.5 volts and 4.5 volts. Are the voltages across the light bulbs equal to the battery voltage? No, the battery voltage is 9 volts. Is the sum of the voltages equal to the battery voltage? Yes, 4.5 volts plus 4.5 volts equals 9 volts. So they sum up together. Measure the current in the circuit we just did. How does it compare to the current when there was only one bulb? It's half of what it was. It was 0.9 amps, now it's 0.45 amps. Okay, increase one of the resistances to 20 ohms. So I'll increase this one to 20. So use the slider, increase it up to 20. Okay, we still have 9 volts across both. But across this guy now, we only have 3 volts. We had 4.5 before. And now across this guy, we have the other 6 volts. Remember Kirchhoff's loops, the voltages have to sum up to 0 basically. So you got 9 volts going one way, then you got 6 volts, minus 6 volts, minus 3 volts, so sum up to 0. All right, so we got, so this guy, the bigger one, this is the 20 ohm, remember, this is the 20 ohm. This guy is hogging more of the voltage. Why? Because it takes more energy to get the electrons through this one because it's a greater resistance. Okay, measure the voltage across the 2 resistors. How do they relate to the voltage from the battery? They still add up to the 9 volts. It's instead of 4.5 and 4.5, because they're both 10 volts, now one's 10 volts, but the other one's 20 volts, so now the 10 volt only has 3 volts, and the 20 volt has 6 volts. Which resistor had more voltage dropped across it, the 20 ohm or the 10 ohm? The 20 ohm had more voltage across it. Measure the current around it. That's not going to change. Well, it goes down because we've increased. See, it was 0.45, now it's down to 0.3 amps. So it went down because we increased the resistance. Instead of the total resistance being 10 ohms plus 10 ohms equals 20 ohms, now it's 10 ohms plus 20 ohms equals 30 ohms. So yeah, the current went down. Okay, measure the current. Does it change or does it stay the same? It went down. Okay, it went down from what it was. Oh, but around the circuit it stays the same. It's still going to be 0.3 amps everywhere around the circuit. Okay, now we want to put these guys in parallel. Let's see, we can put this, no, I don't want to do that. Let me click here. Here, let me pause this so you don't watch me do this. Okay, now we have our parallel circuit. Now across the battery we still have our 9 volts. Across this guy here we have 9 volts. Across this guy here we have 9 volts. Now they're both back to being 10 ohms. They're both back to being 10 ohms, 10 ohms, 10 ohms. I put the 20 ohm one back to 10 ohms. All right, so we have the same voltage. Now what about the current? Coming out of the battery, we have 1.8 amps. Going into this guy, we have 0.9 amps. Going into this guy, we have 0.9 amps. So the current splits right here. Half of it goes through this 10 ohm resistor, and the other half of it goes through this 10 ohm resistor. It recombines over here. Let's make sure. Yes, 1.8 amps going back into the battery. Okay, so so the voltages are the same. All the voltage from the battery is the same voltage we have across both of those guys. The reason is this battery is holding all of this at 9 volts. It's holding all of this at 0 volts. Okay. Measure the current as it leaves the battery. We just did that. It was 1.8 amps. You can hit rewind or go back a little bit if you don't remember. Measure the current going through each resistor. That was 0.9 and 0.9, right? Yeah, it's 1.8 coming over here. It was 0.9 and 0.9 through both of these two. So these two added up to this. Okay, how do they compare to the total? Well, they add up. They add up. Change one of the resistors to 20 ohms. Measure the voltage across both resistors. Did they change? Okay, so we want to. I'll make this one back up to 20. I guess the key is to slide it close and then use that to get it exactly right. So now that guy's 20, this guy's still 10. All right, we got 9 volts across this guy still, and we've got 9 volts across this guy still. We got still 9 volts from the battery. So the voltage is still going to be the same. They're all parallel. Voltages stay the same. Okay. Now what about the current? Okay, now we, instead of having 1.8 amps, we only have 1.35 amps coming out of the battery. We still have our 0.9 here because this resistance didn't change. Well, we doubled this one, so now this went down to 0.45 amps. So 0.45 amps plus 0.9 amps is going to give us 1.35 amps. So we made this one a greater resistance, so less current's flowing here. See how these guys are moving a little bit faster than these guys are kind of trudging along? Okay, that shows you. So more of them are going to go this way. Okay, so measure, so let's see, the voltages did not change. They're both 9 volts. Measure the voltage through the 10 ohm, that was still 0.9 amps. And the 20 ohm, that went down to 0.45 amps. Are they different? Yes. If so, which resistor did more current pass through? The 10 ohm, because it's a small resistance, path of least resistance. So it got more of the current. The smaller one get more of the current. How did the two currents, I'm getting tired. How do the two currents compare to the current from the battery? They add up to the current from the battery, okay? And then this is the last one, Faraday's law. So what we'll do is we'll come over here, we'll go back. So Faraday is down. This is one I forgot about. I'm too tired to do it now. I may do a quick little video on it tomorrow. Okay, we went Faraday's. But I'm tired now, I don't want to do anything. Faraday's law, it's right here. Let's have both loops. What does that do? That's what we already have. Let's have both loops here, okay? So they're separate loops. One's got 4, or separate coils. One's got 4 loops, one's got 2 loops. Okay, so let's go down and do this. Okay, we clip on it, so yeah, we have both of them. Move the magnet slowly into the n equals 4 loops, and note the brightness of the bulb as well as the deflection of the galvanometer indicator. Try to do the same with the same speed through the 2 loop. Was there a difference? So I'll take this and I'll move it slowly. Try to move it slowly. Okay, slowly. It's a little bit of deflection. Light bulb gets kind of bright. Let's do it this one. Okay, I'm moving, try to do it the same speed. Watch the light bulb. I don't know. Put it to you this way. This one obviously is supposed to give you the greater deflection and the brighter bulb. But it's hard to do them at the same. Okay. All right. Move the magnet slowly into move the magnet. Okay, as well as deflection. I try to do the same speed through the 2 loop. Was there a difference? There's supposed to be a difference. It's hard to do it so you see a difference. Move the magnet slowly into the 4 loops. N equals 4 loops. Remind yourself of the brightness of the bulb and the deflection of the indicator. Then move the magnet much faster. So this one you can see. This will be a lot better. All right. So we'll go down here. We'll move it slowly in. Slowly in. I'll move it fast in. Whoa. Move it fast. Move it slow. Not much. Slow, not much. Move it fast. So look at the needle is pegging all the way at the end when we do that. Okay, so move the magnet slowly into the, so yeah, then we did it faster. Was there more brightness with one compared to the other? Yeah, the faster we moved it, the greater the brightness was. Was there more deflection? Yes. With the faster we moved it, there was way more deflection. So we're converting mechanical energy into electrical energy. This is some mechanical energy, not a whole lot. This is a lot of mechanical energy in comparison. Okay, if you move the magnet into the coil and just leave it there stationary, what happened? The word was we put T-H-E-I-R there. I don't, there, like there stationary. I don't, it doesn't make any sense. All right, so here we'll do it. It's stationary now. Okay, so I move it, here I am, boom. Now remember what's happening here. The electrons do not like the fact, see, the electrons in here are happy. They're happy, the world's the same, nothing changes, days go on, everything's the same. You came along and changed their magnetic field on them. So they start to move to try to cancel that out. Now you leave it there. What happens? The electrons will say, okay, we're happy. We'll just have to get used to this new way life is going to be, the new world order. So then they stop moving. So you got to keep this in motion. You got to keep this in motion to keep the electrons moving and trying to cancel out what you're doing to them. So nothing happened. What happened to the indicator? The bulb was dark. The indicator stayed at 0. Bulb is dark, indicator is 0. Which way does the indicator deflect when you move the north pole of the magnet into the loops? To the right or to the left? Okay, so we'll move it into the loops. That's out of the loops. Move it into the loops, it moved to the left. Move it out of the loops, it moved to the right. North in to the left, north out to the right. Okay, north pole into the loops, it moved to the left. And then which way, when you pulled it out, it moved to the right. To the left in, to the right when we pull it out. And now we're going to switch it around and have the south pole here. So we move it in. Oh, when we moved the south pole in, it moved to the right. And when we moved it out, it moved to the left. See, that's opposite of what this guy did. Move it in, it moved to the left. Move it out, it moves to the right. South pole, move it in, it moves to the left. Move it out, it moves to the right. Okay, so then that's these guys here, and that's everything. That's all the answers. Okay, so you just want to, you fill this in sometime before Saturday at midnight. Turn it in, and you got your full credit. I may try to go back. I forgot about this. I really wanted to do this one, but I forgot. I wanted to do this one on refraction. I'll tell you what. Maybe I'll make a short little video tomorrow. Let me call it quits for now and upload this.